All right. Week 5. So I posted this announcement. There is, I think, nothing special this week. So I released the marks for assignment 1 last week. There are still some late submissions. I still need to assess some late submissions. I will do it tomorrow, most likely. So all the marking will be done by tomorrow. I will release a sample solution once all the marking is finished and all the late submissions are done. So it may take a week or so until I can release the sample solution. And then I can also release the actual tests, automatic tests, and you will see they are based on the same test that you had the chance to try yourself. And I saw that many people got full marks, so well done for that, for the automatic test. There are a few who didn't get full marks. Some of them got 0 marks because they didn't, the Python wasn't correct. I mean, didn't run, that kind of things. I saw some people who use ChatGPT or whatever, and wrongly, so they failed the test. So at least try to make it work for this. So it's not just copy and paste the result. You need to understand what it's doing. And you need to say when you use it. So if somebody has used ChatGPT or Copilot or whatever, and you don't say it, if I find out, then you get some penalty. Because you need to say it, how do you use it? That's what we say. So, okay, that's for assignment 1. Assignment 2 is being released. I talked about it last week. So if you have any questions, maybe we can talk about it today at the end of the lecture. Can talk more about that. And the content of assignment 2 is all that we have seen so far. There is nothing new, I think. So as you know from the assignment 2, is the material from up to last week, basically. Today is going to be a different topic, and you will see. I'll talk about it in a minute. And I think that's all. So yeah, today's topic is going to be object detection and segmentation. So this part here. So let's go through it. So as usual, there will be some theory for the first hour, and then there will be, oh. Why it doesn't let me to project? Oh, okay, now. All right, okay, now you can see it. Sorry about that. I should look behind as well sometimes. So what was I saying? Oh yeah, as planned, as in previous weeks, we have 1 hour of the theory, and then maybe half an hour on the practical, and then after that, probably we'll finish in an hour and a half, or maybe not. So let's see. You can ask questions. I can talk about assignment, and we can see what we can do. So this is a completely different topic. So image segmentation, object detection. So far, we have been focusing on image classification. Now we move on to the next thing, or the next 2 things. So now the reading, it's, there is some very good material on the PyTorch book, but it's very advanced. So, and it's in 3 chapters. So all these 3 chapters, I'm going to talk about it on 1 lecture. So it's more things that, if you want to know more, read those things. You probably want to read instead from here to get the material. So all the material is basically from these 2 books. This is more advanced part. So, but it's good that you want to know more. There are many different kinds of object classification, image segmentation. So I'll talk about some of them here today, simple ones, but there are more ones that you can see in all these advanced part. If you want to know more, I will talk about it again on advanced unit, advanced vision and action. We'll cover that later. So here you just get the idea of what it is, what is the technology behind object detection and segmentation. So here are some examples of tasks, the most common tasks for computer vision. And we have seen the top two ones, which is image classification. So there are two kinds of image classification. One is the single label multi-class classification. That means assign one label to the image. So in this case here, there are three possible labels: biking, running, swimming, and the label is biking. Cycling, I would say. But anyway, it says biking here. So then in multi-level classification, the task is to assign several labels to the image, not just one. For example, bike, person, tree, that's what you see here, but there are no cars, no houses, and no boat. So there are three labels: bike, person, and tree. Right? I guess it's American because I would call this bicycle. Bike, I don't know. Cycle? Anyway, so these two are the same thing. We have been focusing on the single label, and that means that on the final layer, you have one neuron per class, and then you pick the neuron with the highest probability, right? So that's what we're doing so far. Like in the MNIST, you would there are 10 neurons at the MNIST. I mean the handwriting number recognition task that you have used in the lectures and the practicals. So there are 10 numbers, so there are 10 categories, so there are 10 neurons, and at the very end of the classification layer, each one is going to return the probability of being that particular class. And then you pick the one with the highest one. That's what we do. So if you look at the code, you will see there's an argmax, or find the maximum and get the one with the maximum. That's to find the best label. In multi-level, you just pick all the neurons which has some probability higher than 0.5. So it's a slightly different activation function. In here, we use the softmax activation function, which is the one we're using so far in this unit, which in PyTorch, you have to make it specific on the model because the loss function is going to automatically apply softmax and then do the loss function. So we don't have to do it, but it is an implicit activation function. In multi-level classification, the activation function is more like for two-class activation, which is a sigmoid activation. It's a different activation function. So identify yes or no for every neuron on the final layer, yes or no. So what's the probability of that being the label or not? And there can be multiple labels with probability higher than 0.5. In this case here, there will be the sum of the probabilities is 1 of all the neurons. In the one here, multi-level, the sum is not 1. You don't try to make it 1, so maybe several neurons with probability of more than 0.5. Like in this case, it will be 3, so the sum is more than 1. When you do the math, you will see. So yeah, it's basically the same task, just it's different activation function, a different loss function. And then the same architecture. So these are the ones we're having so far. Today, we are going to look at two other kinds, image segmentation and object detection. Image segmentation in this case is to identify the regions of the image that correspond to some particular category. In this case, is the blue category and the red category. Blue is for person and red is for bike. So, and this is all the pixels in the image which correspond person to person, so they are labeled as person, and here all the bits all the pixels in the image which are recognized, classified as bike, right? And then object detection, the task is to identify objects, and that means to assign what is called a bounding box, which is a square, a region, a square in the image that corresponds to the object. In this case, this one person, another person, one bike, another bike, and one tree. No, street lamp. Oh, yeah, it's a tree too, but no, it was a street lamp. I see here, street lamp, there. So apparently, in this example, the model is not trained to recognize trees, but it's trained to recognize street lamps, bicycles, and people, and maybe cars and other things. Okay, so the output is going to be these multiple bounding boxes. And we are going to see how that can be done. And you're going to see it's very much based on what we know so far, just modify the final layer in some particular ways. We're going to see here. So image segmentation. So in contrast to image classification, the task now is going to be to label every pixel of the image. It's going to be as many labels as pixels in the image. So image classification is basically one label for the entire image, one or multiple, depends if it's multi-label or single label. For image segmentation, every pixel is going to have a label. So you can see that it's going to be much more complexity, right? The final classification layer is not going to have as many neurons as labels, but as many neurons as pixels and labels, times labels. So it's a much larger number of neurons. We're going to see it later. Okay, so there are actually two flavors of image segmentation. One is called semantic segmentation, in which you have the categories like bike, and person, and background. So there were 3 categories here, actually, not 2. There were 3. There were 3, is bike, person, and background. So there are 3 labels here. So in semantic segmentation, the task is for every pixel to say what category it is, bike, person, or background. On the instance segmentation, if there are multiple bicycles, each bicycle have a different label, like bike 1, bike 2. So in the previous example, well, I'll go to the next one. Yeah, here, to the cats. So on the first image on the left, this is semantic segmentation. The task to identify cats or background. There are 2 categories: cats, background. So green is cat, and I guess blue is background. In instance segmentation, every different cat will have a different label. So there are, in this case, 5 different labels for cats and the background. So the task of instance segmentation is harder than semantic segmentation, not because there are more tags, there are more, but that's not the complexity. It's because the number of tags is not known a priori, right? You don't know how many cats are going to see. It can be 5, 20, 200 cats in there. So up to now, we had a fixed architecture. Each node represents one label to give. In the case of instance segmentation, you cannot do it anymore because you don't know how many cats they're going to be, right? So because of that, we don't cover it in this unit. You can read about it on the textbook if you want to, but it's not for the unit. I'm going to talk about the semantic segmentation. It's going to be hard enough to talk about in this unit. Okay, still the idea is going to be very simple if we already know what we know, right? How to classify images. So as I was saying before, for image classification, the final layer has as many neurons as labels. Now, if you have X times Y pixels in the image, there will be X times Y times N labels on the final layer. Right? So you're going to see it's much larger number. So you will see, yeah. So to enable that, then the final layer we'll need to have a feature map or size, basically x times y times n. So that means x row, y columns, and n channels, right? So as we have seen so far, when we use convolutions, the feature map, feature space, is going to be reduced after every convolution. And that's the goal. You try to shrink the feature map so that you distill information. You get the key information, like the embeddings, image embeddings we were talking about last week. So you are reducing the image, and in which now you have a higher level information, more abstract information in the image. But then you have a problem. You have a small image, and you need to expand it again to go back to the original size, x times y, but convolution cannot do that. You need to have some kind of deconvolution, and that's what I'm going to talk about here. You need to find a way to, I would say, undo the convolution, but in a smart manner. You don't go back to the image, you go back to, say, image size, but high level of abstraction, so that it represents the category or the pixel. So we are going to see this deconvolution is actually, I think technically speaking, is called transpose convolutions, but they're also called inverse convolutions, deconvolutions, upscale convolutions. There are different terms for that. So, okay, transpose convolution layer is basically something like a convolution, but it's going to generate a larger size, a large feature space. So if you have this blue feature space, and you apply a convolution of kernel size 3, then without padding stride 1, you would get 4, I think. 1, 2, 3, 4, yeah. So you will get 4 times 4. So in a transpose convolution, if you have the same stride and padding, when you have this 4 times 4 and apply a kernel of the transpose convolution of 3 times 3 with this stride and padding, you will get this 6 times 6 image. So you're going to see how it works. The way it works is apply convolution to a blown up version of the original. You're going to add extra padding in this image, so that when you apply convolution, it's going to be reduced to this size here. So the extra padding makes it larger than this size, and then when you apply convolution, it will be compacted to this size here. So let's see how. So convolutions, you recall, you apply, this is the blue, it's more like a review. If you have any questions, you can ask now about convolutions. So you have this image size, apply this kernel times 3. In this case, add optional some padding. In this case, padding of size 1. It means adding wrapping ones. So one row on the left, right, and column, row top and bottom, column left and right. And then apply the kernel, the convolution, and slide it through. And every application of the kernel generates one value on the output feature space. And in this case, it is 6 times 6 with the padding. I don't think this figure is quite correct, because you have padding 1 and you apply this, or maybe the stride is not 1, maybe it's stride 2. Then, but if this is stride 1, you can see that it would take more than 4 scans to the left, right? So this is 1, and then second, then third, fourth, fifth. I think there are 6. It will be 6 times 6. So this wasn't quite correct image, but hopefully you get the idea. So you do some padding, and then you pass the convolution from left to right and top to bottom, and you get the final feature space here. Okay, a transpose convolution, what we're going to do, the notation in this slide is to have these 2 dots, 2 stars. So the convolution is just 1 star. So this star this is apply this convolution to this. So in the transpose, they use the notation star star. So a transpose convolution then is going to, given some stride and padding, S and P, is going to calculate a new value for the stride and padding so that this becomes bigger. And I didn't quite say it right. So the stride on the transpose convolution is going to be always 1 by definition. But padding, there are two kinds of padding. One is the regular padding, which is going to add a wrap around the image. And I think that's what is called Z in this case. So calculate new padding, Z, which is the stride minus 1. Okay, so it's going to be 1 in this case, so add this one here. And then calculate a new extra padding, P bar, applying this formula here is kernel minus padding minus 1. And this extra padding is going to be inserted between the rows and columns. And that's the key thing in these transpose convolutions. This extra padding is going to be inserted between rows and columns so that you can expand it even more. So in this example, the green represents the original input feature space. And then in this example, Z is 1, P bar is 1. And that means it's going to add this part here. And these gray rows and columns, that's the extra padding being added. So you get this image. And then to this image, so this padding means adding zeros, as we know, right? So adding something just to make it a bit bigger, it's like expand, upscale the image, make it larger, and then apply the convolution filter on the image, which is 3 times 3. Here is already applied once and twice, apparently, so the color is a bit confusing. So apply the filter with stride 1. So stride it and pass it, slide it all over it, and you get the new image. So I'll recap. The key thing, calculate the new values of new padding, the wraparound and the internal padding. I didn't bring my, oh, yes, here they are. Let me just check. Because I might have said wrong what is Z and what is P bar. Let me just check. Z is minus 1, P bar. Okay. All right, okay, yeah. So actually it says here. So Z is going to be the number of rows and can insert between the image, yeah. And P bar is what you wrap around. Okay, I said it wrong before. Okay, and you get this one here. So the idea is quite simple. Have a question? Yeah, you have a question or all fine? Yeah. In here or the previous one? Z and P bar, right? Insert Z zeros between. Step 2. Sorry. Yeah. So on the first here, it was Z. So insert Z zeros between rows and columns. So I don't know if you can see the colors well. in the image. It's not very clear, but it is green and gray. I don't know if you can see the colors. It's difficult to see. So the green is the original images, original pixels, and then you insert. So in this case, Z is 1. So that means interleave one row of zeros between the original values and one column. So this is Z is 1, Z equal 1. Right? And then here P bar is going to be 1 as well, and you have this pattern here. Is that the question? Okay. Are there questions? No? Okay, I'm just reading here because I think I said all this already. Yeah. This is important. A transpose convolution does not undo a convolution, so the output is not the original image, right? It's the original size of the image, but the contents of the values of the output are not the same as the input at the beginning. Otherwise, well, you're not doing anything, right? So the goal is going to be to upscale, to make a larger feature space in which now each pixel hopefully has some more high-level information, more abstract information. So applying the filter, so the output is not, you don't try to like put an analogy, you have an image and you compress it, and then you uncompress it to get the same one again. We're not trying here. We just want to, when you uncompress, you get the same size, but not the same image, right? So they only undo the resizing of the feature map. And this is good for image segmentation because now you can actually apply a series of convolutions, and then you can apply a series of deconvolutions so that you can undo the size, the resizing, and then you end up having the same size as the original size, but the number of channels, you can make it adapted to whatever you want to, because you recall that you can specify a layer of several convolutions. Each one is going to generate one channel in the final image. So you can do the same with deconvolutions. You can have a layer with multiple deconvolutions. Each one is going to generate one channel on the final feature map. So you have what is called a U-net architecture. It has a U shape. And this is a real architecture. It's been used. So this is something proposed for image segmentation. So you have, in this case, 3 channels, 96 times 128, that should be the original image. And then you start applying convolutions, and as a result, you will have a smaller size of the image, but typically more channels, right? 3, 64, 128, 256 channels, 512 channels, and 3 times 4, the feature map. So it's very small area, but very deep, many channels. And that's what happens typically when you apply convolutions. You want to add more and more channels and reduce the feature map, so you have more abstract information. And then you can apply transpose convolutions that undo step by step what has been done before. So this one is converting from 6 times 8 to 3 times 4. Now applying this deconvolution from 3 times 4, from 3 times 4, you get 6 times 8. Number of channels can be different. It's going to be depending on what you want to have at the very end. But the actual feature map space needs to be same as the one here, 6 times 8. And then at the next deconvolution, same as the one here, 12 times 16, and then 48 times 64, and then 96 times 128. And then at the end you have original size, and then as many channels as labels you wanted to have. Right? So you are, in this case, you are gradually reducing the number of channels until you get the number of channels you want, the number of labels that you want to have, 21 in this case. Okay, this particular example is a bit more advanced. It does a bit more than that. The actual transpose convolution will take as input also a skip connection. We saw the skip connections last week in ResNet, residual connections, in which you sidestep some part of the network. In this case, actually, it does make sense to take as input to here this one and then what was the state before here, right? Oh, sorry, or after here. So this state, put it here as well, and this one here, and then the same here. So basically, each deconvolution also receives as input a copy of the output of the mirror convolution. In that way, it has more direct access to the information at that particular level of resolution of the image. So I had this skip connection, but we are not going to use this in the example. We just do this mirroring without the skip connections, and you get quite good results already. Okay, one more example here for transpose convolutions. When I tried this link before, it wasn't working, and it looks like that this post has been removed, has changed, and I haven't found it. So if you happen to find it, send me the link, because I couldn't find it. But anyway, it's taken from this defunct link. This was from last year. So one example here, stride 1 and padding 0, then you have original image here. And I suppose the kernel is size 2 times 2. So you have, it was p bar, k minus p minus 1, and then z was, I think, s minus 1. Stride is 1, then mean that z is 0, so there is no interleaving. Yeah, there is no interleaving nodes. But then p bar is 2 minus p0 minus 1 is 1, so you have a wraparound of 1. Apply this filter, you would get this result here, which is 3 times 3, a bit larger. This other example here is stride 2 padding 0. So now you have the new z is going to be s minus 1, so 2 minus 1 is 1. So you have interleaving ones. So in this case, because only 2 times 2, you add 1 row, 1 column. If it was 3 times 3, you have 1 row here and 1 row here, and then the third row. Right? Okay, so you have the new value, the new padding in between, and then the new padding around, which is k minus p minus 1 happens to be 1, because k is 2, p is 0, minus 1, so it's 2 minus 1 is 1, so you have 1 around. After applying the filter, you get this size, which is a bit larger. Okay, so that was one trick, I would say, to do image segmentation, how to have these many labels, so rows times columns times number of classes. So that's by applying deconvolution. The other trick you need to do, it's not so much a trick, but you should not use pooling. So in image classification, you normally have convolution and sometimes pooling. So pooling is good when you want to find some invariant, some pattern, no matter where in the region, you want to find some patterns. But in this case of image segmentation, you do care about where the pattern happens. So the pattern happens here or there, on which part of the image, because you want to go back to the pixel that determines, which is classifying the class for that particular original pixel. So the location matters, so pooling is not a good idea. It's going to destroy information about location. So you don't use pooling for image segmentation. Instead, you might want to do striding. So stride, stride with a larger value, so to make it a bit smaller. because strides still are preserving the location, because you have also in the filter to try to step some rows and columns, so you still keep information about the location. Pooling can destroy the information about location, where the pattern happens. Okay, you will see this example in PyTorch, so I will skip this. I'll do a notebook later. But any questions here? No? All right, so then we move on to object detection. So no questions, now different topic. You have to, erase what I said before, put new information, no? Okay, so object detection. So now the task is to assign a label, sorry. Image classification, the task is to assign a label to the image. In object detection, the task is to find a bounding box, or a bounding box for every object that you want to detect. So this bounding box is basically a square. Basically means 2 coordinates. It's going to be the coordinate of the center of the box and then the size of the box on the, so it's 1 coordinate, sorry, and then the size, like the height and the width of the box. So there are multiple ways of doing object detection. The one I'm going to show here is not the first one, but I think it's the simplest one to explain, and it's a very popular one. It's very popular because it's very fast. The accuracy might not be as good as in other places, other approaches, but it's very fast, so it's very useful for real-time object detection. For automatic car navigation, they will use things like YOLO. YOLO on the LiDAR sensors and so on. But YOLO is a way to detect on real life objects. So in YOLO is it stands for You Only Look Once. That basically means there's only one neural network which is going to be used for the entire task. In previous approaches, in YOLO, they will have multiple stages, which will give you very good accuracy, but might take a few seconds to do the whole process. In YOLO, it's much quicker. You just do one pass of the neural network, and then it will return all the bounding boxes. So the way it works, you have a regular network, as we've seen so far, convolutions. And then the final classification layer is not like 1 neuron per category, or is not 1 neuron per pixel per category. Now it's something different. It's gonna be called what is called the object detection and classification head, and I'm going to show about it later. It's going to identify, is basically one for every possible bounding box. What are the, 1 neuron for the coordinates, x and y, and size, and okay, you will see it on the next slide. So this is YOLO. I'm going to talk about YOLO version 1, the first one, which is the easiest one to explain. Currently, I think we are in the version 8, if I recall well. So it has been changing in time. So in YOLO version 1, this was the actual architecture from the paper that described the system, and there is nothing really complex. So you have all these convolutional layers, max pool layers, every now and then, right? And then you have some final classification layer, so some final hidden layers, and then the final head layer, which is going to classify the objects. I'm going to focus on this part here. So the original paper, the size of the image was 448 times 448, and it's going to reduce to 7 times 7. So that's the final feature map, 7 times 7. And then there are, in this case, 30 channels. So let's see what the channels look like. So on the final feature map, is 7 times 7. And that's each of these elements, it's a grid. So each of these elements, 7 times 7, is going to represent one cell in a grid that divides the image. So it's going to divide the image into 7 times 7, so seven rows, 7 columns. And each cell is going to represent, one element of the grid, and it's going to try to detect a bounding box in there. Do that make sense? Because I'm not sure. I was talking a bit strange, so maybe I'll drink some water. Feel better. So I'll try again. So you have 7 times 7 at the very end of the convolutions. So that is effectively dividing the original image into a grid of 7 times 7 boxes. And each cell in the grid is going to try to identify a number of bounding boxes. So it's going to find bounding boxes which are centered in there. In this example, we are showing 2 bounding boxes. So this is like 6 times 7 or 5 times 7 grid. And there are 2 bounding boxes. And these highlighted cells in the grid are the ones in charge of detecting the bounding box shown in the image. So basically trying to find bounding boxes which are centered on that particular part of the grid. So it doesn't matter if the actual bounding box expands farther, larger than the original area of the cell. As long as the center of the bounding box is in the cell, it will try to detect it. So in this example, it's detecting these 2 bounding boxes, one centered here, one centered here. And for every bounding box it's going to try to detect the size. So the horizontal size and the vertical size, here and here. So that means that each cell will need to contain at least 4 neurons, so 4 channels, basically. One for the X, one for the Y, one for the width, one for the height, and more. One more neuron that represents what is the confidence that this box is containing something. Because it's going to be for every box in here, even all the ones here, every cell in this grid, they all try to find bounding boxes, but maybe this particular element from the grid, it will find a bounding box, but they will say, oh, the confidence is 0.01. I'm not very confident that the bounding box I'm highlighting here is a good one, right? So in this example, there were 2 bounding boxes in which the confidence was higher than 0.5, which are the ones shown in here. So that means then 5 numbers, so X, Y, width, height, confidence, and then as many neurons as labels that you want to classify. For example, you want to classify between butterflies and, flies or whatever. So like 2 different kinds of objects, it will be 2 labels, right? It will be a regular case of classification. So that's what I think is being said on this slide here. So for every YOLO grid cell, each bounding box, this is not quite, yes, it's accurate, yeah. So each cell is going to predict several bounding boxes, B. The default is 2 in the original paper, so each cell on this grid will try to identify up to 2 bounding boxes. Only 1 in this case, but up to 2. And then each bounding box is going to be represented with 5 numbers, which is X and Y coordinates, height and width, confidence, and then as many labels as number of classes, right? And that's all. So you have then N times M times B times 5 plus the number of labels. So it's quite a large number of labels. It still is less than image segmentation because you have a smaller grid. Okay, so let's look more about what it really means to try to detect these numbers. So you have, for the x and y coordinates of the center, is relative to the center of the grid cell. That means its value is between -1 and 1. So 0, 0 means right in the center of the cell, and then -1, -1 will be, I don't know, the bottom left corner, I think. So that means that the activation function for these two numbers, for these two neurons, needs to generate numbers between -1 and 1. Now, if you look at the regular activation functions, it's between 0 and 1, the one we've seen so far, like the sigmoid, softmax, and so on. So you have to use a different activation function for this one, which happens, so anyone will do as long as it is between -1 and 1. So the one chosen is the hyperbolic tangent, which I'm going to show a drawing here. So this one here, as the number of the input, of the output of the neuron changes, then after the activation function, you get a value between -1 and 1 using this shape here. And this kind of curved shape usually is very nice. It's smooth, and it's very, very good for gradient descent. So it's a good choice of activation function. You want to have between -1 and 1. Then, for numbers to identify the height and width, that's between 0 and 1. So in this case, you use the regular sigmoid activation function, which has this shape, which is very much like the hyperbolic tangent, but now the range between 0 and 1. So this is hyperbolic tangent, sigmoid tangent. Again, for the confidence factor, sigmoid again. And then for every value, okay, this is interesting. Depending of how you want to represent the labels, you want to find only one label or multiple labels. Typically, it's only one label, but you might want to say, oh, here the same box is for butterfly and something else, I don't know. So, but more common case will be only one label, so that's then applying like a sigmoid, a softmax activation on all the cells. So you have this part here. So on the 7x5 grid, for our example, you have as many channels as 5 for the bounding box, and then as many as labels, and here are the activation functions. So this basically means that the actual implementation is a bit more complex than we've seen so far, because so far we only apply one activation function, the same one for all the cells on the funnel head. Now is, depending on which cell you're looking at, it's a different activation function. So it's a bit more involved, but it's just kind of tedious programming. It's not really that difficult. You need to make sure that, okay, activate this region with this one with this region. So we not do it here, but you can see that this is what you need to do. All right, any questions here? No? Okay, and the final part of object detection is the loss function. So if you recall, loss function is going to measure the error of prediction. And you tried, so the system is going to be trained so that it will minimize the loss. That's the goal. In this case, because now we have multiple, objectives for each cell, for each channel, they have like a different goal, right? To detect the coordinates or the level or the confidence. So now the loss function is more like for a multitask loss function. It's like a combination of multiple loss functions, because you want to make sure that you are measuring the error of prediction of each different components of the final layer. So it becomes a bit more complex. So this one here doesn't go to the exam. You see this symbol here. Means that doesn't go to the exam. You just need to know that you will need to have a custom-made loss function, which is a specialized, complex one, for this particular task. So I can just quickly say what they are. So basically, for identifying the object presence, so the confidence of the system, that is going to be basically like a cross entropy. So it's 0, 1, is there or not. So these two combined, I don't know why they put it separate, but these two together is the regular cross entropy. And then the object classification loss is the regular categorical cross entropy, this formula here. So now you have two losses combined. And then you need to find also the loss for the bounding box, the coordinates of the bounding box, which are all numbers. And I think it's on the next part here, which is basically it's more based on the mean square error. So you find the difference between the predicted one and the correct one, square to make it positive, and then you sum all of them. So okay, it's the sum square, it's not the mean square error. The sum square error, here this is some square root in between, but basically it's trying to find a formula which will be, when there is less error of prediction, the value is smaller. When there is a larger error, the value is larger. And you look at this, it's a difference, so it's going to be in function of the difference of prediction. So the final loss is combine all these different separate losses with some formula like this one here. Okay, as I was saying, you don't have to know these formulas, just need to know that there is a very specialized formula for the classification head for the object detection. Okay, so YOLO is very fast, but it has some problems that you need to know. One is, this is YOLO version 1. YOLO version 1 predicts a maximum of B objects per grid cell, and the grid is 7 times 7, so if 7 times 7 is times 2, it's going to find this many objects, but if there are more, it wouldn't find all of them. Also, this is a very coarse resolution, 7 times 7, so it will make it hard to detect small objects because we'll be lost about all the information. We apply all these convolutions, and then the small objects are kind of lost on the information of the image. Also, the YOLO object detection is applied to the last convolutional layer, means that some information that existed here after all these many convolutions might be lost. So you might want to use some skip connections so that all the information is there. So YOLO version 1 did not have skip connections, so as a result, it will not work well. It will have some error of detection. And I think that's about it. Yeah. So there have been other approaches that will try to address some of these problems. So YOLO V8, for example, it's much better than all this. And you're going to use YOLO V8, as I recall, in the practical for this week. So I'll stop here. We take a break, 5 minutes break, and then we go to the demonstration, and then we can talk about assignment if you want me to talk more about that. So, right, so 5 minutes break, so at what, 2 times 2 past 3, we continue. Okay, let's continue. So just a reminder about these questions I'm putting here towards the end of the lecture notes. They're actually exam questions. So these questions, they are taken from past exams, or they are inspired on past exam questions, or they could be next exam questions. So it's, I think it's, I'm going to go through them again on the exam review, but I'm just going to go through these questions and past exam questions. So it's, I think it's good for you that you see you can answer these questions. What I'm putting here is just a way for you to assess the quality of the new, ChatGPT or your favorite AI-generated tool. You can ask them the question, see the answer, and then see if you can identify any possible mistakes or inaccuracies from there. Typically, they are very good answers, and I think every month is better. So I haven't tried this year, really. But last year, when I tried this, they were already getting very good answers. So actually, it can be a good study tool. Just remember that sometimes they make mistakes. So must be careful about that. So, but you can see if you can try to find the answer yourself, or try to see if ChatGPT will get it right or not. We'll see more about LLMs and on the text part, and you get to see more how the technology works for those systems, and then you will understand why they can make these mistakes. But I think it's good for you to try now, these tools. That's why I do encourage you to use the tools for coding as well. It's becoming better and better, so I don't see why you shouldn't use them. So, but you need to understand how it works. I mean, how the code generated, how to modify, how to make it ready. If you just copy and paste, it might not just work. And I've seen that some assignment one solution, which is copy and paste from ChatGPT and not even bothering trying to make it pass the test or something. So anyway. So, okay, the task in this notebook, I'm going to use Jupyter Colab because their GPU is better than mine. Yeah.
I have a question. So when we try to do it in VS Code and try to use CUDA, do we need to install anything, or it should work by itself if you have the GPU?
You mean for this particular one?
Just whenever we try to use the device equals to CUDA.
Oh, okay. So in your laptop, do you have CUDA, first of all? So you have a GPU which is CUDA enabled.
So I've got my PC at home, which has the NVIDIA GPU.
Okay. So sometimes the actual version of the GPU might or might not be accepted. So the PyTorch will have a list of GPUs which it recognizes. If it's not in that list, then you need to check on the discussion forums, because sometimes you might need to reinstall from the source. So if you use Windows and you use, say, this, I call this pip install torch, is fetching some pre-generated images, and sometimes they are not designed for some GPUs. So you might need to actually use the source code, which is C++ or whatever, and compile it on C, and then it can be quite complex. So try to use the instructions from PyTorch, how to install it. But yes, you need to install PyTorch, and you need to make it CUDA aware. But I think by default, it's like that. Actually, let me just have a look. No, sorry, not by default, but it's very simple. They have very nice grid. I don't know if you went to here. Oh, yeah. So how to install PyTorch? So you can, okay, do I have Linux, Mac, Windows? I want to use conda.pip from source, and I don't know, this one. So I will use pip, it's the easiest one. And Python or Java, well, Python, that's what we use here. CUDA, you need to see what GPU you have. You need to see if it can support the latest CUDA, use it. If not, then you can use an earlier one. And if it is too old, then it might not support any of this CUDA, and then it might not work. So but what I what I do actually, I go for the latest one. If it doesn't work, I'll try to this one. So that's what I do. So it actually takes quite long to install. So it's not just a few seconds. But yeah, and then just copy. So you can see when I click on different options, then this is changing. So then you just run this, and then it should work. So try it. If it doesn't, you might want to try this CUDA or this one here, or if not, you might have to go to the source, which then it becomes more complex. Yeah? Any other questions? I think we can leave those questions for later anyway. That's not so much for this particular topic. So, okay, so the task is going to be identify pets. So let's connect this. In the meantime, we're going to go to this link here. Okay, so we're going to use the Oxford 3T pet dataset, which is a dataset which is used for tasks about object segmentation, object detection. So you have these two different things. So we're going to work on the part of segmentation, but you can use it also for object detection, for training and testing. So yeah, for segmentation, we're going to have images and then masks. And this mask has 3 regions, so you need to try to regenerate this mask. So there are 3 channels, and that means being the object, so being the animal, being the edge or the border between the background, and being the background. So they have these 3 different regions. So the task is to detect these 3 different regions. So download the data. So those links are directly from here. Some of I think these links here. So they are using a format, a conversion format called tar and gzip. So if you use Linux, which is what it is in the backend or Google Colab, then you can use these instructions. If you use Windows, depends on your computer, you might need to unzip twice, because there are 2 different compressed formats concatenated. So when I try to my computer, when I download and have to unzip, and it will create this image.tar, and you need to unzip or uncompress again, and they will create the images. Okay, so already been done. So let's see what we have. So we have, okay, this is downloaded files, and then you have the images. This is, okay, all the images here. I realize this MAT, interesting. That's why. Okay, one thing I haven't really talked about in this unit, because it doesn't belong to this unit, it belongs to 6200, is about data exploration, data preparation, data pre-processing, and so on. So what you really need to do is, when you download the data, is this the right data or not? What format do they have? Do I need to clean the data or not? I'm not doing any of those things here, but you should do it. And now I realize I should have done it, because this file here is .mat, it's not JPG. So MAT, I think, is a matrix which is used in, what is, I forgot, it's a famous statistics package, which I now got off my head. But it's a different format anyway. So that means that it might not be able to read this file well, or might get an error when reading the file. So you need to be careful with these things. But anyway, so you can see you have a folder images, and then all the images in there, all JPG, though I realized when I was reading the files that sometimes there are 3 channels, sometimes there are 4 channels, sometimes there are no channels. It's grayscale. So it becomes a bit annoying. So you have to handle all these different formats, and you will see what I did in this example. Okay, so this is the images, and then the annotations is the masks. This is the try maps. So let's go to say this one here. Okay, you don't see it here, just because it happens to, it's a matrix of n rows, n colors, and 3 values, 1, 2, and 3. So they are all very dark. So it's also dark here. So what you can do is what I did here. So first of all, let's load the images, load the path of the images. So this code here is just listing all the paths for the images and for the try maps. That's the maps, the target mask. And then I got the list, and now let's just read one image and display it, which is here, this cut here. And now let's read the mask. Okay, we have to post-process the mask so that it can be displayed. So what I'll do is read the image and then do this multiplication. As it happens, when I apply imread, the result is between 0 and 1, and it needs to be between 0 and 2, right? 0, 1, 2. So what I did in this case is I had to kind of try several times until this one actually worked. So multiply times 255, and then subtract 1, and they will get between 0 and 2, 0, 1, and 2. So let's apply this, and now read the mask that corresponds to this image. So this number 9. And then just to make sure, let's display all the unique values to see, must be 0, 1, and 2 are the possible values. And then display. And then unique values 0, 1, 2, so looks okay. And this is the display of the mask. So you can see, looks like 0 is the object, 1 is the background, and 2 is the contour, the border. Okay, so let's create the data loader. And in practice, this is the most difficult part, really, because it depends on the actual data. So each data is different. So you need to, might have to try several times until you get it right here. So in this case, the image had already been, the data, input data is already been loaded into 2 lists, this one here. So we're going to use that information. So we're going to define a data set that takes the image paths and the target paths, and then at initialization, we just load them into the internal variable so we can access to them later. So that's one. And then the length can be the length of either of these 2. So this one, why not? And then get item is the more complex one. So if you recall, in get item, the input is the index of the image, and then the output must be the image ready for PyTorch and the labels. Or the label, label or labels of the image. So in this case, the image, okay, we take image path, and this is the target. And then here we read the image. And now I had to do a couple of checks. If the shape has only 2 numbers, that was a grayscale image. So we will need to basically add 2 channels. And what I did here is just copy the value of the same values to all the other 2 channels. So that's what we're doing here. The NP stack is going to stack the same values again and again, twice. So you get basically the 2 extra channels so that it is a grayscale, but the same value for red, green, and blue, right? And then I would have to then select the first 3 channels and remove the 4th one if there was a 4th one, because it happens sometimes there were 4 channels at the transparency channel, so remove that one. And then rescale to divided by 255, so that it is between 0 and 1. And then resize, so that it is for the range that you want. Hello? Okay, now can you be more quiet? Okay. So resize the image to the desired value, which is 200 times 200. And as you recall, I hope you recall this part here, when you read the image, it is in the format of rows, columns, channels. But for PyTorch, it needs to be in the format channels, rows, columns. So we have to swap the last component of the tensor with the first one. So we can use transpose for that. And we can see here first the element number 2 in the tensor, and then 0 and 1. That means channel, row, column. Okay? And then for the target, we call to this function read target, the one defined here. We're just going to do some rescaling so that it is between 0 and 2, which is what we want, which is great. And still, we want to resize the mask to the right size, 200 times 200. Once you have all that, then convert to a tensor, move it to the device, and then for the images, and then for the target, tensor, making sure is the type is integer long, otherwise you have some error messages, and then to the device. Right, so this part here actually took me quite a while to make it right because of the characteristics of the images, and so this is the most time-consuming part, and that's the one you spend most time, typically on any task. So make sure that the data pre-processing is right, is ready for PyTorch. Any questions here? No? Okay. So, okay, now you have the data set. Now let's create the data loaders so that they can, so a data loader, what it's going to do is to, each time you call to the next step on the loader, it will return one batch, which is ready for PyTorch. So before running the load, before creating the loaders, let's do a partition of the data. So this part here, I think I just asked ChatGPT, do a partition. How do you do it? How would you do it? And then they came with this code here. And it's very simple. So what it does is, given the list of image paths, shuffle it. So that you know, any possible order in here is lost. So all the possible categories are kind of interleaved. So that's the best thing to do. You shuffle. And then you shuffle the targets, and you use the same random seed on both of them so that the shuffle is identical in on the 2 different lists. So this is important, to have the same random seed. Otherwise, you shuffle this, you shuffle that, with different random seed, and you get, they don't align, the mask, the target with the images. So be careful with that. And then validation samples, 1,000 for validation, why not? And then you take the first part of the shuffled list is for training, and the last part is for testing, right? Look at this. So it's from the beginning until the total minus the number of minus 1,000. So here, and then for validation from just the last 1,000, this part here. Okay, once you have this, now you can define the data sets and data loaders, and here you use train input paths, train target paths, which are the ones from here. Shuffle equal true for the training data, and shuffle equal false for the validation data. And we said why before, because for validation, you might want to keep the same order if you want to do any error analysis. You want to plot, say, the first 5 errors, and you want to make sure they are all the same ones and you do the plot. Okay, so I haven't run this. So now this is running. And here, just double checking that everything is okay. So here what I did is take the training data loader, training data set, and then take the sample 10th, and then it's going to return the image and the mask, so get the image from the sample number 10, and then display the shape, and display some pixel from the image to make sure it's within the range that we have. This is what I call defensive programming. You're making sure that everything is okay as you do programming. So the shape is right, so 3 channels, 200 times 200, and then the pixel on the channel 0, row 10, column 10 is this value, which is between 0 and 1, so it seems to be okay. Okay, so now let's go for the architecture. So we're going to have the U-shape architecture. We're going to have convolutions and the transpose convolutions. So for each convolution, it's going to have the convolution. I didn't talk about this, but this is what the textbook says, that sometimes you might want to insert this, which is what is called batch normalization, which is a way to speed up convergence. So what it does is to normalize the weights of the neural network, so it is between some particular set of values, and it doesn't get too big or too small, and that will normally make it easier for the gradient descent algorithm. So, okay, I didn't talk about this, so I just said it now. You don't really need to know it, but it's here, so I just say it now. And I'm going to try what happens if I uncomment this. This is was just from the textbook. So if I comment this, what happens might be slower to train. It will take longer or might not converge. And then activation. So each convolution is like that. So I'm going to define some helper function called conv. And then for each transpose convolution, you have the transpose and the activation. So let's define these two. And then get model is a sequence of convolutions, which is our definition of convolution from here. And then transpose convolutions, as defined here. And if you look at the way it's defined, it's trying to make clear that the transpose convolution is undoing the size of the mirror convolution. So 256, 256, and then 256, 128, which is this one here, 128, 128, 128, 64, 64, 64, and so on. And then when there was a straight 2, it's straight 2 here as well, in the mirror image. And then sometimes you need to add some extra padding, which they call output padding, and that's because of some, when you apply convolutions and the number of rows and columns is not divisible by whatever is used by the convolution, then the feature space is a particular size, and when you apply the deconvolution, then it will not go back to the original image, but because the original image was not divisible by the original value, right? It's like when you do a division with a number and you want to multiply again. and then you don't get the right value again. So you need to add sometimes some extra values, which is this extra padding, which you add, it's like the remainder in the division. So add some extra padding so that you make sure that the final image is correct. So how to identify when to do this or when not? Well, trial and error. So you can basically try, if you get any error message, then you might want to add some add padding equal 1 to make it to avoid this rounding problem when you upscale, go to the larger number. So, okay, this is all the same. So let's run this. Let's display the summary. And you get this, after the convolutions, the feature map is getting smaller until 25 times 25, sorry, here. And then when you apply transpose convolution, the feature map is getting higher, larger, until you get 200 times 200, which is the size, well, from the beginning. And then 3 channels at the end, because that's the number of labels you want to have. It happens to be the same number of the input channels, 3, that's just coincidence. In this case, there are 3 labels, 3 channels as the output. Okay, so let's try again. So suppose that we didn't do this. And we try. Then you will see that here, the image, the feature map is 49, should be 50. But just because of when you apply the transpose convolution, sometimes it doesn't go to exactly the original number because of these rounding problems. So that's why when you get, if it says 49, okay, add 1 more, 50. If it says 48, add 2 more, until 50, and so on. So was it here? Yeah. So now it's fine. Okay, so all this is same as before. And then let's see if this works. When I tried just before coming the lecture, for some reason I got an error. And I think something maybe to do with some temporary problem. So let's hope it's going to be okay now. If not, well, this takes quite long to run. So I'll let it run in. And then if all goes fine, then you would get this plot. So, oh, one more thing. So far it's working, which is great. So one thing, this code here it's taken from the previous notebooks with some modification. On the previous notebooks, we used the accuracy to monitor the quality of the validation set. But now accuracy doesn't make much sense because you have a mask. It's not a number, the output. It's not a label, it's a mask. So accuracy is something more complex to calculate. So I just use the loss as a way to display the quality of the validation data. So that was a small difference, which is, yeah, this part here. So to calculate the loss, I just for every batch, and then run the model on the test data, and then apply the loss function, right? And how to do things like don't apply gradients because at test time, and then the model needs to be set to evaluation, not to training, and things like you need to send, after you find the loss of the data, then move it to CPU so that you can do the next thing. So all these things, you know it just by trying. And you get an error, and you say, oh, well, why is the error? Then it's typically because of these things. It needs to be on the CPU or in the GPU and so on. Nowadays, you can basically ask to to Google Colab or whatever, explain the error, and it will tell you. It's much easier than before. So, or you can just ask ChatGPT or ask in the discussion forums, why do I get this error? And it will tell you, oh, that's because it needs to be in the CPU, not the GPU, and so on. Okay, that's good. This is working. It was working just half an hour ago in my office. So, okay. So here you see that the train loss and the test loss, they are quite similar. The test loss at some point starts not to get much better, but you can see that maybe you can try some more epochs and you will get better results. But it was starting to plateau. So soon you will be able to stop training. But I left it here. The loss was already getting okay. You can see it was starting to overfit. But as the loss was still going down, I would let it run a few more epochs. But each one takes, how long? 1 minute in this case. So it's going to take 20 minutes to run this. So I'm not going to do it. I might let it run in while we do other things. So after we have this, then let's apply. Let's see what happens if you apply on an image and predict the mask. So let's read the image. So let's get the number 9 from the, I think, no, not really, just from the data, the number 9, which is this one here. And if you notice, this is the number 9 of this variable, which is the same one, number 9, from the same variable, but it's different image. Can you tell why? Yeah? Shuffle, yes, we did a shuffle, which is somewhere around here. Actually, I didn't know. I thought, why, what's happening? Until I realized that we have shuffled the variable here, but as a result, now the image number 9 is different. So, okay. So now this is the image. So let's read the image, and then scale, transpose, make it ready to send it to PyTorch. And then let's get the best model. The best model said here, right? So if the loss of the trace data is the minimum so far, save the model. That's what we're doing here. So let's load the model here. And then the evaluation, no gradient, and then apply the model on the image. Oh, okay. This part here is because the model expects a batch of images, not one image. So you need to wrap the image inside a batch. So a quick thing to do it is to use the unsqueeze, which is to add one more dimension to the data, is wrapping into one more. So it's a batch of one image, and then send it to the device, and then you get the result in test predictions. And then on test predictions, apply argmax, making sure that you look at the axis number 1, because axis 0 is the batch, axis 1 is the channels, axis 2 is the rows, axis 3 is the columns. So axis 1 in the channels, you want to find the maximum across all the channels, right? Yeah, I think so. I mean, think about it, but I think that's what you need to choose here. And oh yes, yeah, of course, yes. Yeah, across all channels or the final, yeah, now I think something is wrong, yeah. All the channels from here, yeah. So the maximum, there are 3 channels, so one for each level, so the maximum from there, yeah. Okay, and right, and then get the first one because it's a batch, what you're having here. So let this play it, and you'll get this. So this mask is not perfect, but it's getting there. So this is the original image. This is the mask, so it looks like getting close. And it was a very simple network, well, very deep, but simple. And actually, there are 2 million parameters in this. So it's getting quite large, but it's still simple in concept. And well, I'll leave it here. So any questions from this? You can see that the theory is all not that difficult. The only complexity was, well, one is to define the data set, because that depends on each different application. The other one is being a bit careful about the architecture so that you have the convolutions and the transposed ones in a mirror fashion. Then, if you look at the textbook from PyTorch, they show you how you can apply this skip connection, but for that you cannot use the sequential construction. You need to use what they call the functional construction, which we haven't covered here, so I'm not going to talk about it here. But look at the book if you want to. And it's not that difficult to add the skip connections, and then you get probably better quality. Oh, by the way, in this example, I have removed this. What is it? Yeah, oh, where? The normalization. So I'll let it run in. I'll see if the result is much worse or something. So far, the test loss is going down, which is great. And let me just compare with Epoch 8. Similar, okay, all right. Similar loss, okay, so maybe this batch normalization wasn't really helping much. But anyway, I'll stop here, and do you have any questions? It's your time. If not, we can go back to the assignment 2, and talk about it again. Do you have any questions on that? So no question on this, so no questions here. Assignment 2, you want me to talk anything about that again, or are you happy with everything so far? Okay, so remember the deadline is week 7. So 5 of May. And remember, it will take time, a lot of time to generate images. So for the last task. So don't leave for the last minute, otherwise you will fail the last task. So it's up to you. Okay? So, okay, so we stop here then, and next week will be the last week, which is more some practical concepts about image classification and computer vision. So see you next week. But I'm going to stay here. I want to see this. Sorry about that. Hi. Okay, so wait, I forgot to say that today, but yeah, I still need to reassess the latest submission. So just tomorrow I will do it.
When I cloned it in GitHub, it said like it failed, but my code ran.
Yeah, it's GitHub is not working now because I ran out of quota for the tests. So I'm running the test on my computer. So if you run the test on your computer, if they work fine, then it should be okay.
It said okay.
Okay, that's great. So you can check when you get the mark. If you see that the mark doesn't match your test, you can tell me.
What are the lectures that is covered by assignment 2? Like is it up to lecture 5?
Sorry?
Like the scope of assignment 2? Like what are the lectures we need to study? Is it up to week 5?
Yeah, until last week. Yeah.
Until week 4?
Last week. Today's week 5. Yeah, until last week, week 4.
Until week 4 only.
Yeah.
So not 5, 6.
Yeah, so from there's nothing on what we covered today.
Yeah, because I'm a bit behind, so I have to study.
Yeah,
the
yeah. No,
lectures.
there is nothing on. You can see there is nothing from we talked today on the assignment.
So on the
And for next week there is nothing. I don't think there is anything. I will say a few tips next week. Practical tips. I mean, some of them can be useful for the assignment, but it's not really necessary.
Studying the content up to week 4 is enough
Yes.
to do
Yeah.
it. Okay, thank you.
So I did run this entire thing, so this is the,
Oh, right. Oh, you have a good GPU.
I mean, it's not really, I used Colab as well. So.
Okay, all right. So did you comment out this batch normalization? Or?
I mean, not,
Because this is what I'm doing here. I commented out this one here, and I'm curious to see what happens because on the books they put this one just because they didn't quite justify much. So I just copied it, and I thought maybe it's not really needed, and running again. And so far, there is no difference on the results.
I actually kept batch normalization as is. I didn't comment it out.
Okay.
And ran the
Okay.
test.
Mhm.
So after running this
Yeah.
is the curve
Yeah,
now.
yes,
so
and you can see it still can go down on the test. Test loss can still go down. Yeah.
Mhm. And then, like, if you read the image, then this is the mask you get.
Mhm.
So
Yeah. Mhm.
it will be considered okay, good, not good.
Well, it's not perfect, so
It's-
you can run more, but it's getting something. Yeah. So actually, again, I didn't say that, but in the practical, you're going to use the model you saved. You can apply it and try it out in the practical on new images. So don't delete the model. You can always use the one I upload on here.
I have this saved. I also downloaded it on my laptop, so no problem. I can use it. So, okay, I'll then use it on the practicals and see how it fares. So,
Yeah.
okay, that's all I want to show. That's all.
That's good.
Okay.
Yeah,
Okay,
it's good. It's
Thank you.
working. Yeah.
Okay, thank you.
I want to ask about on the assignments too. On the part C, I want to touch for sure. They told us about I need to generate about at least one image.
Yeah.
Maybe I can generate more than 100, 200, something like that, right?
Yes, at least 100. Yeah.
And
For,
we
for,
don't-
for each one, for
Yeah,
rock,
rock,
paper,
what-
so rock, do many of these. No?
Yeah. So does it mean we don't care about the background, just focus on the hand, right? When use our webcam?
Well, try out. I would say, maybe, I could have said that, and nobody asked that question. But if you look at the images from the original data, they have a gray background. So it would probably get better results if you have gray background.
Okay.
Right? But I don't know. So you can try this. It's possible because you have 100 images. If your background is always the same in all the images, and then maybe it will learn that to forget or to change the background.
I see.
Well, I would say try to make them I suppose, as similar looking as the one from the data.
Okay.
Otherwise, you're making it more difficult for the system. It doesn't really matter. You get the mark the same. One
Yeah,
or the other,
yes.
it doesn't really matter, but I think you feel better if you get,
Yes.
if you get better results.
Okay.
But I'm not looking into like beating, the one with the top score will get more marks, and I'm not looking at that.
Okay, got it. Thank you. See you next week.
Right.